In this video, we're going to begin to learn how to calculate work in one dimension. I've brought back the problem from a Newton's third law video of two blocks. We have a pushing force of 24 newtons that pushes against a 2 kilogram block that pushes against a 10 kilogram block, and the surface on the ground is frictionless. I want to know the work done by every force and the total work done on each block after the system moves 6 meters. Now I suppose I could go back and look at what my answers were for the forces, but it's probably just as fast and better practice to calculate them again. First I'm going to look at Newton's second law on block 1. There are two forces on block 1, the pushing force and the contact force of block 2 on 1. Here's a free body diagram. I've set positive x to the right. Translating this using my one-dimensional notation for vectors, magnitude of the pushing force minus the magnitude of the contact force of block 2 on 1 is equal to the mass of 1 times the acceleration of 1. Now these two will move together as 1, and so that means their accelerations will be the same. So I'm just simplifying without the subscript, since the acceleration of 1 is equal to the acceleration of 2, which I will just call a. Looking at block 2, there's only one force on block 2, and that's the contact force of block 1 on 2. Here's my free body diagram, and I will also set positive x to the right. The scalar relationship for that just gives me the magnitude of that force is equal to mass 2 times the acceleration of 2, which I've just called a because it's the same as the acceleration of 1. I notice that the force of 2 on 1 and the force of 1 on 2 are Newton's third law force pair, which means their magnitudes are the same, which I'll just call F. If I substitute, then, this F into here, I get this relationship. The pushing force minus mass 2a, acceleration is equal to mass of 1 times the acceleration. I can solve that for the acceleration. Mass 2 times a on the other side, factor out the a, divide both sides by mass 1 plus mass 2. I get this relationship, and I can plug in numbers. The pushing force is 24, the total mass is 12, and I get acceleration of 2 meters per second squared. I can then use this relationship to find the force, which is 20 newtons. And that's the same for both of those forces, so I now have all of the forces in the problem. So how am I going to calculate work? Now all of these forces are constant. They're not changing in time, they're not changing in position. Everything is in one dimension, so I have a really simple relationship where the work is just the force times the displacement, where I use my one-dimensional vector notation. First I need to know the displacement. I'm told that the displacement is 6 meters. I know from the context of the problem that that is a vector to the right, so now I just need a coordinate system. I'm going to set up my positive coordinate system to the right as well. Note that this coordinate system is not independent. If I want to calculate the work due to each of these forces, I need to calculate my displacement each time with the same coordinate system in which those forces were defined. So if I had, for example, set my positive x to the left for block 2, I would have to use that coordinate system when I calculated the work from the displacement for block 2. But since all my coordinate systems were to the right, I'll set my displacement coordinate system to the right. Everything should be fine. I can now calculate the work due to the pushing force, the magnitude of the pushing force, which is in the positive direction. The displacement is in the positive direction, so a work of 144 joules. Next, the work due to force of 2 on 1, which is in the negative x direction. So I represent that by a negative 20 times 6, or a negative 120 joules. The work due to the force of mass 1 on mass 2, that force is in the positive x direction, so that's represented by a positive 20 times 6, or positive 120 joules. Now we can find the total work. Since there is only one force on mass 2, we have already found the total work on mass 2, 120 joules. The work on mass 1, the total work, I've represented by T, is then equal to the sum of the work of all the forces on mass 1, which were the first two, so that's 144 minus 120, or 24 joules. Does this make sense? We see that the work on mass 2 is a lot larger than the work on mass 1. Both of these objects are moving together, so they're going to have the same speed, we know that work is adding energy to the objects. And this is telling us that it takes a lot more energy to make a 10 kilogram mass go the same speed as a 2 kilogram mass. I can think that might make sense. Also, what about the other way to calculate net work for mass 1? What is the total force on mass 1? The pushing force was 24, the other force was 20. That means the net force was positive 4, times 6 meters to the right is 24 joules. That is also consistent.